It may seem odd at this point to be aborting a chapter which calls itself encryption. Now, what have we been talking about all along? Haven't we studied encryption? Well, the fact is that cryptographers usually use the term encryption for a primitive whose goal is data privacy. What we've seen so far, block ciphers and pseudorandom functions, are tools that help you get data privacy, but by themselves, they're not quite what we'd like to call encryption. So here we start then with the next step. We're going to discuss what privacy means, what we'd like to call encryption, and how the tools we've seen earlier can be used to give rise to it. The word symmetric refers to the fact that here we are looking at a setting where the sender and receiver share a key between them. Okay, so any cryptographic primitive has multiple elements to its description or content. One of them is what we call syntax. Syntax just tells you if you want to specify this, if you want to write code for it, if you want to describe it mathematically, what do you have to give? And another component, security, emerges also later. A symmetric encryption scheme is described by three algorithms. So when you say you have a symmetric encryption scheme, you're saying you have described or specified these three algorithms. The first is a key generation algorithm. It takes no inputs and its job is to spit out a key. It's a randomized algorithm, and most commonly it'll just pick a key at random from some space, and most commonly that space is all strings of some length. So for example, many schemes are AES based, so your key is just a 128-bit AES string. That algorithm is run once, it does its job and it goes away. And then something outside the scope of the syntax of the scheme, it's assumed that magically the key is communicated to sender and receiver. Now what the scheme gives you is an encryption algorithm. This takes the message and the key, that's the symmetric aspect, that the key is used for encryption, and it returns a ciphertext. And this $sign here indicates that potentially this algorithm is also randomized. That means even for a fixed message and a fixed key, there may be many different ciphertexts coming out, and we'll see why that's important. This just indicates that the transmitted ciphertext could be seen by the adversary, but that's not part of the syntax. The final element of the syntax is this decryption algorithm D. It'll take this ciphertext and it'll take the same key used for encryption and deterministically return an output. If all goes well, that's the same message that was encrypted, but the decryption algorithm may decide that it doesn't like this ciphertext and return this special symbol bot to indicate something went wrong. Key generation is randomized. It's not going to be possible to have any meaningful security if it isn't. Encryption may be randomized, and we'll see that for security we'd like it to be, but decryption is always deterministic. Okay, so whenever you want to describe a scheme or you see a scheme described, you better see these three algorithms. Before we get to security, the first requirement on encryption schemes is what's called correct decryption. And that just means that decryption really does reverse encryption in the way one would expect. So if I have fixed a particular key, doesn't matter which one, anything that could be spit out by key generation, and I encrypt a message M under that key to get a ciphertext, and if decryption is then applied to that ciphertext with the same key, it ought to reproduce the same message that we started with. This is important because otherwise communication doesn't make semantic sense. It has nothing to do with security, just about communication correctness. Formally, we could write the requirement on the algorithms by this equation. So what it says is take any key that may be output by key generation and take any message, encrypt the message under this key, take the resulting ciphertext and decrypt under the same key, and you want to get back the message. Now, there is a probability around this because we have allowed encryption to be randomized. And so what this is saying is that no matter what randomness is used by the encryption, this should always be true. The probability of it being true is 1. We've talked here about a message space. Usually a scheme will have some set of messages which it is able to encrypt. And when we give specific schemes, we'll usually say what that space is. Okay, so let's try to now build these encryption schemes. And as we discussed right in the beginning, in the introduction, encryption, at least if you want to do it well, is not something that we kind of put together in some ad hoc way, just starting from scratch, whereby you write down some encryption algorithm in a few minutes and it's going to work. Instead, we're going to use the Lego approach and build up. So we're going to start from something like a block cipher and extend it to get encryption. So for the next few slides, we'll let E be a family of functions. Remember, that means it's a 2-input function. It takes a key of length k, some input of length n, and returns an output of some length l. Usually, it'll be a block cipher. In that case, the input and output lengths are the same, but it needn't be. You will see cases where the scheme does not require that restriction. We will be breaking messages into blocks. So when you have a message X to encrypt, we will let X sub I be the ith block and view X as a sequence of blocks and let M be the number of blocks. How long is a block varies. It's usually either N or L, depending on the scheme, and we'll specify that when we get to the scheme. The key generation algorithm will always have the form that it takes a key at random from the key space of the family of functions, and that becomes your encryption key. So since the syntax of the encryption schemes requires 3 algorithms, we've just fixed the first one. What we're talking about here are called modes of operation because they are ways of building symmetric encryption schemes on the back of families of functions or block ciphers, and they're referred to more specifically as modes of operation off E or off the block cipher. That isn't the only way to perform encryption, but it's the most common and widely used way. If I'm handed a block cipher already, and the assumption is I am, and I'm also willing to assume that it's secure, let's say it's PRF secure, then it would seem, well, we have an encryption scheme already. If I want to encrypt a message M, I have a key K returned by the key generation algorithm, which just picked it at random from the key space of the cipher. I can just run my message through with E sub k and let C be the ciphertext. And I send that across, and it can be decrypted by applying the inverse block cipher. So what then is the problem we're trying to solve with symmetric encryption? Isn't it already done? Well, it's something that at first glance may seem quite simple, just that messages that we actually want to encrypt in real life or in applications are not 1 block long. Remember, the block is just something like 128 bits, but we have files, videos, emails, chat communications, whatever. They're long. So you could say that really a mode of operation is about encrypting long messages given the ability to already encrypt short or n-block messages. Looks easy. It turns out it's not actually that easy, but certainly there are obvious, easy suggestions for how to do it. And the natural one is called electronic codebook mode. So this is one mode of operation. What is its job? It's to deliver a symmetric encryption scheme based on a block cipher E. So we're given E, and we're now going to specify the algorithms of the symmetric encryption scheme. One of them we already saw. We know that this algorithm just returns a random key K whose length is appropriate to be used as a key for the block cipher. How do we perform encryption and decryption? We have a long message M. We break it into blocks. The length of a block is the length of an input to the block cipher. We have M blocks in the message, let's say, and then we just run each block through the block cipher with the given key and get a ciphertext block. And what we return as the encryption of M is the entire sequence of ciphertext, right? And so that's encapsulated in pseudocode over here. How do we decrypt? Well, we use crucially the invertibility of the block cipher. If you know the key, you can run this block cipher backwards. So the receiver obtaining the ciphertext will run E backwards. It can do that because it has the key and just recover the messages as written here. The first thing to check is the correct decryption requirement hold? It's pretty clear that it does because we know that this really does invert the block cipher. Notice notationally that there are two E's. There's an E that's the block cipher here and a script E that's the encryption algorithm. These are not the same objects, although they coincide when the message is just one block long. But it's good to keep them apart and not somehow conflate them in general. So if we consider the security of electronic codebook mode, maybe naively or historically one would think it looks pretty good. Why might one think that? We might do that by thinking about the adversary's ability to recover the key from plain text and ciphertext. Well, a good block cipher would resist that type of attack, and so encryption could be done without fear that the adversary would recover the key. Maybe that's a good starting point to think of it as secure. The interesting element of encryption as a goal arises when we start seeing that that's not the right metric, and there are weaknesses in electronic codebook mode which arise independently of the block cipher. Even if the block cipher is a PRF, or in fact anything you might want it to be, there are inherent weaknesses. And what we're going to look at is what are they, and also why should we view those as weaknesses? And that's sort of the learning point of how we measure security and what our requirements are. Okay, so what is the weakness? Well, it's quite simple. It's just that encryption being deterministic, if I twice encrypt the same message, I'm going to get back the same ciphertext. So if I have two messages, M1 and M2, which happen to be the same, so will their encryptions. Remember here we're talking about encryption under a fixed key, which has been chosen and fixed by the sender and receiver, and that's not changing across these encryptions. Also remember that a message is a sequence of blocks. So when I say M1 and M2 here, each of them consists of some number of blocks, say little m. So look at how electronic codebook mode encrypts. It'll just run the block cipher here and get these. Well, if M1 and M2 are the same, when you do it here, of course, you'll get back the same ciphertext. So not only is this obvious that if M1 equals M2, then C1 equals C2, but it seems like, of course, what else could possibly be true? This goes back to our intuitive or historical sense of what encryption is, coming from substitution ciphers, which is it's some kind of code. For every message, there's a corresponding ciphertext once you fix the key. But this is actually, as we'll see, not desirable. This is a property that's actually a privacy weakness. So when we assess whether something is a privacy weakness or not, or start getting a sense of it, often the way we do that is we look at possible applications or usages. And being creative about these usage settings is how we grow to better understand what requirements we want from our crypto. So the application setting I'll consider here is that there are only two possible messages out there. Call them yes and no. Maybe they're encoded as a string of all ones and a string of all zeros, each being one block long. How might that happen? You just may be in a setting where everyone, including the adversary, knows that there are only these two messages, and the entire point of encryption is to just hide which of the two it is. For example, buy or sell a stock, you're just sending instructions. Or there's some kind of proposition and everybody's casting a vote. Well, the vote is just yes or no. So everybody knows that these are the only two possible messages that could be sent, and privacy is just about hiding which of the two was sent. In this case, although the script E and the normal font E are in general different, they become conflated because the message is just one block long. So encryption is merely application of the block cipher to the message being either 1 or 0. Okay, so what I now claim is that knowing that this is the setup, there is no privacy at all afforded by this encryption method. So for example, suppose that the messages are votes, and suppose you have some kind of polling station where people come, lots of people, one by one, they cast votes. And at the end of the day, the polling station encrypts the votes under this key K and sends them to some tally center. So the setup we would want is that the adversary sees the ciphertext C1 and C2. Of course, it doesn't know the key, but the key is unchanged in computing those two ciphertexts. Let's say M1 is the first vote cast and M2 is the second vote cast. And we would like that privacy of these votes be maintained, meaning nobody knows whether these votes are yes or no. Now, we again get creative or paranoid, if you like, about what is the application setting, what is it that the adversary might know or do. And let's assume here that the adversary is actually one of the voters. So it casts the first ballot. It knows what M1 is because that's its own vote. Let's say it's voting yes on this proposition. So it knows M1 is yes. However, a priori, it does not know what M2 is. M2 is the vote of some neighbor or colleague or whatever, and its interest as an adversary is to decrypt C2 and recover M2. And our claim is that it can actually do that despite not knowing the key. How does it do that? It just compares C1 with C2. Remember, it sees both ciphertexts. If they match up, if C2 equals C1, it must be that M2 equals Y as well. M2 equals M1. Why? Because this block cipher is a permutation. And so if C1 equals C2, then the inverse of C1 under the block cipher equals the inverse of C2 under the block cipher. But also conversely, if M1 is not equal to M2, the permutation property of the block cipher says that C1 is not equal to C2. So if C1 is not equal to C2, the only possible choice for M2 is no. In either case, just by looking at this equality, your adversary has completely decrypted C2 and completely recovered M2. So that's a violation of the voting privacy. This is a commonly used picture to illustrate more graphically what the weakness with electronic codebook encryption is. The difficulty is another way to express it, that whenever you have a certain block, it gets encrypted the same way regardless of its position in the message. Here we are encrypting the pixels of a penguin image. And what you see is that since a particular color always gets encrypted the same way, effectively the colors are still visible. You can effectively make out the outline of the penguin, right? And this is another good illustration of why electronic codebook is bad. Okay, so having seen that, one might think that this is unavoidable. No encryption scheme can possibly avoid problems like this. Why is that? Suppose I have an arbitrary encryption scheme, E. No matter what it is, it takes a key K, it takes a message, returns a ciphertext. And suppose I encrypt two votes, M1 and M2. Everyone knows they're either yes or no. And just as before, we know the first vote is a yes. And we're trying to figure out what M2 is. So let's try the same strategy. We just compare the ciphertexts. If they match up, it must be that M2 equals M1. Why is that? Because correct decryption ensures that E is uniquely decryptable. And if they don't match up, it must be that M1 and M2 are different. So this is an attack which claims to recover the second message. If this attack were correct, it would say that unavoidably encryption is going to leak this type of information. So the attack is in some sense correct, but only under a certain assumption. The assumption is that the encryption algorithm is deterministic. Whenever you have an encryption algorithm that once you fix the key and message returns a unique ciphertext, this attack does work. But what that tells us is not that it's impossible to get better security, but that we need to move beyond determinism and come up with methods of encryption that are randomized and allow us to circumvent this. And that lesson has been well learned. Basically, modern encryption is randomized. It's not going to be of the form we saw there. But from a classical perspective, this is a kind of novel and interesting idea. What it says is that every time you invoke the algorithm, even with a fixed key and message, it's going to flip coins. And if the same message is encrypted twice, we are likely to get back different answers. So even if M1 and M2 are the same and you encrypt one and then the other, it's possible that the ciphertexts are the same, but it's unlikely. The probability of that happening would be small. What that means is equality is not leaked by looking at the ciphertext. So that's fine in principle. We could think that we have somehow liked to randomized encryption so that this type of property and security hold. But then we have to ask how we might possibly do that. And it is at least a little bit challenging when you realize that you have to maintain decryptability. So encryption now, even given a particular message M and with a fixed key K, will produce not one but potentially a whole slew of different ciphertexts. Decryption, however, has to know how to map all of them back to the same message. So something to think about. Okay, before we go to examples though, it's worth again emphasizing or looking at the historical perspective under which we think we know what encryption is from things we've seen in books and newspapers and so forth. But somehow the layman's notion of encryption is a substitution cipher or a code. And that's inherently deterministic. So saying that your encryption should be randomized is kind of a novel viewpoint that we're coming to here. Okay, so here then is an example of a scheme with randomized encryption. It's again a mode of operation of a block cipher. So we fix this E here as our block cipher, say AES. As before, the key is just a key for the block cipher, and that defines this algorithm here, which picks it at random. And we're just going to say how encryption and decryption work. Again, I take the message and view it as a sequence of blocks, where the length of each block is the length of the input to the block cipher. And now I'm going to run, as before, effectively, each block through the block cipher to get a ciphertext block. The difference, however, is that randomization occurs through this step here. Every time you call this algorithm, it'll pick something called an initial vector at random. It's just some string of length, the block length of the block cipher. It puts that over here. Rather than encrypt the first message block directly, it XORs that in first. And that's what's encrypted to get C1. And that's the reason for the name, chaining, this continues. Before encrypting M2, you XOR this value in, and then you encrypt. And then you get this ciphertext. Now, what the ciphertext is, it's important to note, as returned here, includes this block. So this is C0 through CM. The ciphertext is just one block longer than the plain text. No harm in that, but it's good to remember that. As usual, before we talk about security, we better check you can decrypt. So how do you decrypt? we're going to again exploit the invertibility of the block cipher. And you can see how it works. Let's say you want to get back this block. You take this, you run it backwards through the block cipher, and that gets you here. But you have this because you have the ciphertext. You add it in, and you get the first message block. And that can be iterated as you go along. And this is the pseudocode. Okay. Now, it's an interesting scheme. There are many things you might think about or ask about it. One of them is that even though we did randomization, the randomizing factor was placed into the ciphertext. The adversary knows exactly what that is. It turns out that's fine. We're not trying to hide the randomization, we're just trying to introduce it. This isn't the only way you could do randomized encryption. Another way, perhaps even more natural, is called counter mode. Here we have, again, some E. In the past two schemes, ECB and CBC, we required E to be a block cipher. That requirement is dropped. So most likely it is a block cipher, but it doesn't have to be. So in other words, it doesn't have to be a family of permutations, and this invertibility property doesn't have to be true, and the input length n doesn't have to equal the output length L. To describe the scheme, it's best to start with the picture. So what we do is that when we want to encrypt the message M1 through MN, again broken into blocks, we pick a random starting point. I'll again call it C0, and its length is the input length of the family of functions. And then we just create a sequence of points. Think of this as an integer. We add 1, we add 2, and so forth. So a bunch of distinct points with a random starting point. We run the block cipher or family of functions with this key on all of those, and we call the outputs the P's here. P stands for pad, because what we're going to do is use them as pads for encrypting the message. Each message block is simply XORed with the corresponding pad block, and that gives you the corresponding ciphertext block. So in particular, the message is not involved in inputs to E. It only occurs over here. The ciphertext includes not just all of these, but also C0, because otherwise it wouldn't be possible to decrypt. Okay, and then here's the code. So the loop simply goes through constructing all of these objects. How do we decrypt? And this is in some ways interesting because the perspective behind block ciphers as being the primitive of choice is that the permutation property and invertibility is crucial to allow decryption. But we see here that even without that, we actually can decrypt this for this encryption scheme. Why is that? The decryptor gets the ciphertext, which is all of this stuff. So it has C0. It can thus create this sequence. This is just deterministically created from C0. And it has the key, so it can run E sub k. It has to only run that in the forward direction. There isn't any backward direction. It'll get all these pads. Now if it XORs C1 with this pad, it gets back M1. C2 with this pad gets back M2, and so forth. And that's what this code over here does. Okay, so now we've seen that correct decryption is true. We have another example of an encryption scheme. We can now look at a few details. What does this addition mean? Well, we're starting with a string, and to write x plus I means I first think of this as an integer, add an I to it. That result I'll take modulo 2 to the power n, because conceivably it could get bigger than 2 to the n. And then I just convert the result back to an n-bit string. So that's what this notation over here means. And once I've done that, it's an appropriate input for the family of functions. Another small thing that might be worth noting is that the messages have length, message blocks rather, have length L. So their length is the output length of the family of functions. These blocks also have length L each, so each of C1 through Cm has length L. This block has length N, not L. It's of this length over here. So in this ciphertext, not all blocks have the same length. Okay? Okay, so CBC mode in some ways predates counter mode, but as time has passed, counter mode has become more and more popular and more the one that people use. And there may be a few reasons for this. One of them could be that decryption doesn't use the inverse of the block cipher. That's certainly something that makes it extremely interesting on a technical level. But another is that encryption and decryption are parallelizable. So you can uh, encrypt messages, blocks of the message independently of each other in this scheme, which you couldn't do in cipher block chaining because you had to always know the result of the prior block's encryption in order to encrypt the current block. So this on multi-core machines will lead to quite some speed up. Okay, so the purpose of randomization was hopefully to add security. That's something that we're going to study in a good deal of depth. But at least as a starting point, we might look intuitively to see, have we gained something? And so let's go back to the attack and setting where we have votes being encrypted, M1 and M2 are yes or no. And as we saw, electronic codebook mode failed there. Let's see what happens with CBC. Can we mount the same type of attack? So again, your adversary knows that M1 is, let's say, a yes. It knows exactly how encryption is being performed, but it doesn't know what the key is. When M1 is encrypted, you'll get back a ciphertext of 2 blocks, not 1 block. The first block, according to CBC, is randomly chosen. That's added into here, and then the second block is computed through the block cipher. When M2 is submitted, the process is repeated, with this being freshly chosen at random and added into here and here. And the adversary is again saying, is it possible for me to determine whether M2 is yes or no, in particular by comparing the two ciphertexts over here? If they're equal or not equal, can I use that to learn something about whether the messages are equal or not equal? But you see what happens is that almost always you will get this and this unequal. And as a result of that, whether or not M1 equals M2, these two will also be unequal. So regardless of what the relation between these messages is, the ciphertext is not going to be in any easy way telling you something about the quality of the messages. So you can play with this a bit, but it seems we're making progress, right? We've at least shown that this attack is not going to work. However, these schemes are quite widely used, and this analysis we've seen here is not terribly convincing in the sense that how do we know there isn't an attack? We've just kind of argued that, well, one of the most obvious ways fails, but maybe there's some kind of other attack. And a lot of our effort now is going to go into thinking about how we give some evidence that CBC or counter mode are indeed secure, and that will involve not just figuring out how to give evidence of their security, but figuring out how to formalize what we mean by security in such a way that, for example, this voting application is captured in our formalization. So the starting point for that is to go back to the setting of encryption and consider what are the things an adversary might try to do. This time now we're again back in an abstract mode. So you think of having a given symmetric encryption scheme. It could be ECB or CBC or CTR, but it doesn't have to be. And encryptions are being performed under that encryption scheme, and the adversary is getting ciphertext back. In particular, the sender has a sequence of messages, not just one message. M1 through MQ and encrypted them one by one, possibly randomized due to the scheme being randomized, and the adversary got ciphertext. What we're trying to assess now is not whether the scheme is secure, but first, What do we mean by security? What are the tasks that if the adversary does, we would be upset about? Well, if it manages to find the key K, that would be very bad because it can then use the decryption algorithm, which is public, with this key to just go and decrypt all these ciphertexts and get back the messages. Maybe there's a way to reverse the encryption on C1 to get M1, which doesn't require knowing the key. If so, the adversary gets M1, and that's also a bad thing. But next, what we start realizing is that there are many other things we want to hide, and some of them can seem strange at first, but then in light of our examples, they get more natural. What if the adversary could figure out whether the first and second messages were equal given the ciphertext? That would be a problem. In fact, that's exactly what was the problem with the voting application. So we want to make sure that equality of messages is not testable from the ciphertext. But there are various other things. What if it can figure out the first bit of a message? Should we worry about that or not? And one might say, well, who cares? It's just one bit. But in fact, good encryption ought not to reveal that. And if you actually want an example where it matters, just go back to the voting. So the messages are either all zeros or all ones. If you know the first bit, you actually know the whole message. It could get even more subtle. What if an adversary says, I can figure out the sum XOR of the first bits of M1 and M2. Should we care or not? And the answer again is that yes, we should care, not just because we could think of some application where it mattered, but because good encryption really shouldn't reveal anything about the message. So this is our goal going forward. Something we won't hide is the length of the data. So the number of bits in each message will in fact leak. You can see that in all our modes of operation, it always does. It's difficult to avoid that. We give up on hiding the length of the message, not because we don't want to hide it. It's actually the case that there are attacks out there that exploit the leakage of the length to do damaging things, but because it's technically and pragmatically quite difficult to figure out how to hide it. So rather than just as when we define PRFs, look at some list of properties and try to see that as the conditions making an encryption seem secure, we'd like some kind of game that specifies a master property, and just meeting that is something we can argue and accept as being the security goal in which we're interested in. And somehow this one condition has to imply all the different security attributes we've seen before. If this master property, as I'd like to call it, holds, then a ciphertext really shouldn't reveal anything about the plain text. In particular, you shouldn't from the ciphertext be able to tell whether the underlying messages are equal. You shouldn't learn the first bit. You shouldn't learn the XOR of 2 bits and all those other things. So we'll go on to study things like that. And we'll do that through a technical definition we call INDCP of what this property is. So since this will get pretty theoretical, maybe let me back up a little bit to provide a little bit of motivation for this. And mainly this consists of seeing that the types of questions we're talking about are very much out there. They're things that are asked in practice and reflected in what's used out there. So Stack Exchange is a place where people pose questions of all kinds. There's a cryptography component. And here's someone asking, can you tell me which of ECB and CBC is better and how to decide what to use? Well, having studied this chapter, you'll be able to give a very good, clear answer to that. And you can see also what the conventional wisdom is. As someone says here, nearly anything is better than ECP. So they've understood that and that ECB is bad. By the way, it doesn't mean it isn't used anymore, unfortunately, but it's slowly being eroded out. There are more detailed answers here. So here's someone who really explains the difference by saying exactly how the mode works and different vulnerabilities, and talks about effectively the kind of definitions we talk about. So good information for kind of a practical perspective on the differences between the modes. So here is a government standard. This is the National Institute of Standards and Technology publication on an encryption scheme or mode called GCM. And this is used every day. So if you are using a computer to access pretty much any website, as we've discussed before, you're accessing TLS, right? So remember, this lock here means you're using TLS, your connection is secure, and so forth. TLS uses GCM, right? So you are encrypting your data with GCM every day. Now, GCM has many elements and components in it, but and we can see here, it's also interesting just to see how standards are written and things like that. They have to be careful about a lot of details and so forth. But the point that it's worth noting for us here in terms of motivation is that the encryption method underlying GCM is actually counter mode. They call it GCTR. And here you see, up to changes in notation, the same picture we had on our slides. So CIF is the block cipher, we call that E. This ICB is what we call C0, the initial random choice. INC is the +1 operation. So when you do that, you get what we call C0 plus 1 and C0 plus 2 and so forth by continuing these INCs to get here. You run those through the block cipher with the key K, and the X's are what we call the message N, and these are XORed to this plain text padding block here, and the Y's are what we call the ciphertext C. Okay. So again, just to show you that it's very much out there. We're not asking questions or talking about schemes that are somehow esoteric.